So let's talk about applying quantum mechanics, all the postulates. That postulates are designed by to solve a quantum problem. I mean, when a particle undergoes interaction with the potential,
Sure, let's break it down step by step. The postulates of quantum mechanics are essentially the foundational rules that guide how we describe a quantum system. When a particle interacts with a potential, we apply these postulates to predict its behavior. We use the wave function to represent the particle's state, and the Schrödinger equation describes how that wave function evolves. The potential influences the Hamiltonian, which determines the system's energy and how the wave function changes over time. In short, the potential shapes the dynamics, and the postulates ensure consistency in how we calculate probabilities, measurements, and outcomes.
I mean, when the particle in a potential well, can you formulate the solution using complete quantum mechanics postulates?
Absolutely. Let's take a particle in a potential well as an example. First, we postulate the state of the system with a wave function. Next, the wave function evolves according to the time-dependent Schrödinger equation, which depends on the potential of the well. Third, measurable quantities come from Hermitian operators. For a well, the energy operator, the Hamiltonian, leads to discrete energy levels. We then solve the time-independent Schrödinger equation. This yields allowed energy states and wave functions inside the well. Finally, the probability interpretation means the squared magnitude of the wave function tells us where the particle is likely to be. In short, the postulates guide the setup, evolution, and interpretation of the solution.
So, what do we understand by stating how that particle and the potential well actually works, and how that solution to that problem designed in such a way that it should satisfy all the postulates and the solution gives the results?
What we mean is that the entire process defining the wave function, evolving it, and interpreting the outcome follows those postulates. The potential well shapes the Hamiltonian, and the Schrödinger equation ensures the wave function evolves consistently with that potential. When we solve the equation, the allowed energy states emerge as a direct consequence of the postulates. The measurement postulate ensures that when we measure energy, we only get those allowed values. The probability interpretation means we can predict where the particle is likely to be found. In short, the solution satisfies all postulates. We evolve the system according to them and interpret the final outcomes in line with them.
So, what you are suggesting actually, and when we talk about this wave function, how we can compute it experimentally?
What I'm suggesting is that the postulates give us a clear framework. The wave function represents the state, and its evolution under the Schrödinger equation lets us find energies and probabilities. Now, experimentally, we don't directly see the wave function. Instead, we infer it through measurements. For example, if you measure where a particle lands many times, the distribution of those outcomes relates to the wave function's probability density. Techniques like scattering experiments or photoelectron spectroscopy allow us to deduce the structure of the wave function from patterns in the results. In other words, we calculate it theoretically and confirm it through experimental patterns.
So, for a particle, for the hydrogen atom case, do we do the same method, that is applying all the postulates of quantum physics to this hydrogen atom problem and get the solution?
Yes, exactly. The hydrogen atom is a classic example. We apply all the postulates of quantum mechanics. The wave function describes the electron's state, and we solve the Schrödinger equation with the Coulomb potential from the nucleus. This yields the well-known quantized energy levels and orbital shapes. By measuring spectral lines, those precise energy differences, we confirm the theoretical results. So yes, the hydrogen atom is solved by applying the postulates step by step, and it's one of the cornerstones of validating quantum theory.
And what about those things that help us to understand the complete mathematical picture of that hydrogen atom and that postulates?
The complete mathematical picture comes from putting all the pieces together. The wave function of the hydrogen atom is found by solving the time-independent Schrödinger equation. We use spherical coordinates due to the symmetry, and it separates into radial and angular parts. The radial part depends on the electron-proton interaction, which gives the quantum energy levels, the principal quantum number. The angular part yields the well-known spherical harmonics, defining orbital shapes with angular quantum numbers. Measurement postulates let us interpret these orbitals as probability densities. So the postulates structure the entire process: the equation, the boundary conditions, the quantized solutions, and how we interpret what we measure, all giving us that full picture of the hydrogen atom.
Okay, how can we experimentally see that probability densities there?
We don't directly see the wave function, but we see its effects through repeated measurements. For a hydrogen atom, you can measure the electron's energy by observing spectral lines. To get at probability densities, think of experiments like scanning tunneling microscopy. By repeatedly probing many atoms, you build up a pattern of where electrons are more likely to be. In other words, the distribution of detected electrons matches the probability density. Thus, by gathering many measurements, we confirm the density patterns predicted by the wave function.
Electron matches the probability density. What do you mean by that?
I mean that when we measure a quantum system many times, like detecting the electron's position over and over, those results form a pattern. The probability density, which is the square of the wave function's magnitude, predicts where you're most likely to find the particle. In other words, places where the probability density is large will correspond to more frequent detection events. So the pattern of measured outcomes, where detections cluster, matches what the probability density predicted by the wave function tells us.
So what we have discussed till now, and what one things you like about this discussion?
We've walked through how quantum mechanics postulates, like the wave function, the Schrödinger equation, and probability interpretation, guide us in solving a system like the hydrogen atom. We discussed how solutions predict quantized energies and how experiments indirectly confirm probability densities. What I enjoy about this is how it connects the abstract math to the physical world. It's a beautiful interplay between theory and experiment, and it's always rewarding to see how nature lines up with our predictions.
Okay, and can you suggest some ideas about solving some physical problem in quantum physics and using the complete postulate thing? What things you like the most?
A great example is tackling a quantum harmonic oscillator, like modeling a particle in a parabolic potential. We'd start from the Schrödinger equation, apply the postulates to find energy eigenstates, and interpret the results as quantized vibrational states. Another idea is the quantum double slit experiment. Applying postulates shows how the wave function produces interference patterns while measurements collapse it. What I enjoy most is that the postulates give us a universal language, whether it's a simple potential or something deep like spin-orbit coupling. The consistency of these rules lets us explore everything from atoms to fields, making quantum physics endlessly rich.
Okay, thank you.